Okay, so we're going to have a little bit of fun with these, with applications of these logarithms, and we're going to take a look at half-life and rate of decay. Now, usually when someone says half-life, we think of carbon-14 or some scientific dating process. What we're going to do is we're going to take a look at caffeine in the bloodstream and look at its half-life, and we're going to come up with the rate of decay from the half-life. Okay. So let me go ahead and give you the approximate half-life of caffeine is 5.7 hours. Now, what does that mean? That means that let's just say I started with 120 milligrams in my cup of coffee. Okay, that's a little bit lower than maybe a really strong brew, but anyway, 120 milligrams. That means that about 6 hours later, of course, I'm going to have 60 milligrams in my system, roughly. And then 6 more hours, in 6 more hours I'll have 30 milligrams, so etc., etc., etc. So that's what half-life means. It's the amount of time for a substance to reach half of its, half of its original amount. So what if I just wanted to ask a simple question like this? How much caffeine is in my system, I don't know, 2.5 hours later? Well, if we get the rate of decay, then it actually makes it makes it easy to answer those types of questions. So let's go ahead and create a formula using the rate of decay. Okay, and we're going to deal with caffeine and its particular half-life. So here we go. I want to begin with a formula that has, I'll do it this way, y equals, and we're going to say this is the initial amount, 1 plus r to the t power. Okay, now that's one formula, but I also want to give you another formula, which is this. And what we're going to find out is that those formulas will give you roughly the same answer. Okay, and we'll take a look at that in just a minute. But I'm going to do this two ways. Okay, we're going to get the rate of decay using both formulas. Okay, rate of decay for caffeine in the bloodstream. All right, let's take a look. On the left-hand side here, what we're going to say is, let's just say I start with 1 milligram of caffeine. I want to know how long, I know that half-life means that it would become half as much in 5.7 hours. So I'm going to put the time as 5.7 right there. There's my A. And then I'm going to have this, 1 plus the unknown rate of decay. Okay, so here's my unknown R. And that's what I'm looking for, the rate of decay. And when we say decay, it just means decay is just meaning it's not growing. We tend to label them as either growth or decay if they're exponential. Okay, so let's see. I know that the 1 right here, I don't have to keep it, right? It's multiplying by 1 is just 1. So let me clean it up. Oops. Okay, there's that. And then I have 1 plus r to the 5.7. Okay, now I can't take this to the 5.7 power because of the r, right? I mean, I don't want to do some crazy form of FOIL 5.7 times. I mean, that's impossible. So here's what we're going to do. We're going to manipulate this thing, raise it to the 1 over 5.7 power. Why in the world? Well, because raising it to the 1 over 5.7 means that because we have a power raised to a power, we multiply, and that cleans up the exponent spot. What a deal, right? So now I'm going to just put this in the calculator to find out what the left-hand side will be. Let's see. And I get 0.885, we'll call it 8855. Okay, so now I'm going to subtract 1, and we get R is, let me move some room down here, we get negative 1145.1145. Now, well, what is that as percent? Well, it's roughly 11.45% rate of decay. Whoops, excuse me, rather messy. Negative. Okay. Alright, so about 11% rate of decay. Now, let's take a look at finding, using the half-life to determine the rate of decay, using this continuous, basically continuous decaying equation, formula. Here we go. We're still going to have half the amount that we started with. Or this, by the way, is the initial amount, so I'm going to call it 1. Here's my e to the I don't know power, right? That's the r power. And then this is obviously 5.7. So that's really 5.7r. Okay? Now, I'm going to divide by 1. Remember, this is this cleaning off in front, right? If I divide by 1, then that goes away. And if you needed to do that, we didn't really. Okay, 5.7 r. Now, remember, I'm going to take the log of both sides. It's got to be the, it has to be the natural log. That's going to allow me to bring the 5.7r around to the front, and I'll have natural log of e. Okay, here again, here is my r. I'm trying to get it alone. This actually is the number 1, so I don't need to worry about that. I'm going to divide now by 5.7, divide by 5.7, and I get that r is about, I'm going to say roughly, negative 0.122, roughly, which means 12.2% is roughly my rate of decay. So you notice that these are really close, right? 11 point, almost 11.5 to 12.2. That's not much difference. Okay. Now, a lot of people will use this formula because it's actually kind of models what really is going on. Your body doesn't stop and then take away 12.2% or 11.45% and then stop again and take 11.45%. You know, it continuously does it. So this, a lot of people will use this one and say that it's just it's more accurate, and it is. So that's what we have. We have a rate of decay. All right. So now let's answer some questions about caffeine in the blood system, or in the system. So let's just say I drink the 120 milligrams of coffee, 1 cup of coffee. Okay, 120 milligrams of caffeine. Let me be specific. That's how much caffeine is in it. Okay, in 1 cup of coffee, my particular cup. And I want to know how much caffeine is in my system 1 hour later. Right? 1 hour later. Okay? So let's use this. I'm going to actually use the continuous decay formula. I'm going to use this one right here. I could use the other one, but I'll use this one. So here's what I have. I have my initial amount is 120 milligrams, and I want to know how much is going to be there, right? This is what I don't know. I'm going to want to know how much is going to be there after an hour. So there's E. Now I know the rate, right? Oops, excuse me, I forgot my negative there. It is definitely negative. Okay, so it's going to be negative 0.122. Right? I have to use the decimal version, not the percent version. And then, looking back at my formula, right? 1 hour later, let's go ahead and put that in. 1 hour later, there's the T, 1 hour. All right, this is just a problem in dumping it into the calculator, completely. Just dumping it, let's see what we get. Okay, so about 106 milligrams, roughly, of caffeine in your system after drinking 120 milligrams of caffeine in a cup of coffee. Okay, what about if I wanted to know what happens 4 hours later? In other words, how much caffeine is in my system 4 hours later? Well, I would do the same thing. I would say the initial amount is 120. I'm raising it to e to the negative 0.122, but 4 hours later. Okay, so here we go. Let's find out. And we get that we have roughly 74 milligrams, remaining in our system. Okay? Okay, so let's ask another question a little bit differently. We're using the same decay rate for caffeine out of the system. Let's just say that I want to know when will 95% of the caffeine, right, assuming that I've had that same cup of coffee, 95% of the caffeine, when will 90% of the caffeine be eliminated from my system, right? So changing up the question just a bit. So here's what we're asking in this one. When will 95%, so that means this. It means when will I have only 5% remaining, right? In other words, when will the full amount be down to 5%? So let's take a look. Here's my formula. This is initial amount, there's times e to the RT, right? Initial amount, final amount. What I want to know is when will my, let's just say the 100% or the 1 milligram, however you want to think about it, when will it be just 5%? Well, there's 5%. When will I have 5% in my body? Why? 95% has gone, so that would leave me only 5%. So when will 95% be already gone from my system? When 5% remains, and so that's what I'm going to put in there. It's kind of like half-life. When will I have half of it? It would be a half there, would be 50%, but when will I have only 5%? Okay, so let's take a look. There's negative 0.122, and then again, the question that I'm asking is about t, when. Okay, let's finish this one up. Okay, so let's take a look. Trying to save some time here. So when will 95% of the caffeine be eliminated from my system if I drank a cup of coffee with 120 milligrams of caffeine? So I've placed the rate that we found from the half-life, and I'm looking for the amount of time that it takes the initial amount to become just be 5% of what it started with, what I started with. So okay, that makes you want to kind of wonder whether you should be drinking caffeine past, I don't know, 10 o'clock in the morning. Anyway, about 25 hours, using this information, about 5.7 hours for half-life for caffeine, and just your typical system, right? And of course that varies with metabolism and all kinds of things. Anyway, let's take a look at one more thing. Okay, actually not just one, but just a few things. I want to take a look now at going the other direction. If I have the rate of decay, how do I get the half-life? Let's take a look at that. Alright, let's take a look at now going the other direction. If I give you the rate of decay, or even the rate of elimination of something out of the bloodstream, let's keep, keeping with that idea of something being eliminated. If I say it's a 15%, it is eliminated 15% every hour, then and I ask you, well, what's the half-life then of that? So here's what we're going to do. It's fairly simple. We're going to go ahead and write the formula. Okay, and we're going to say, okay, I want that to become half, and my rate for this particular one, pardon me, is 15%, and I want to know, I want to know how long that takes. That'll be the half-life, right? So let's get this whittled down, and we have 1/2 e to the 0.15 t. Take the natural log of both sides, and we have natural log of 1/2 is equal to natural log of e goes away because it's equal to 1. I'm going to divide by 0.15. 0.15 divide by 0.15, and I get t is roughly, okay, and you're probably realizing, hey, you didn't make that negative, pardon me, that's supposed to be negative. That's because it's being eliminated, right, out of the bloodstream. So that's going to be a negative there. That's going to be a negative there, and that gives me approximate half-life of about 4.6. So about 4.6 hours is the half-life of that substance. Okay, let's do a couple more, and we'll be through. All right. What if we're asked about the age of an artifact given the rate of decay? And of course they would have to tell us, we're assuming, I'm going to go ahead and assume that we're going to use, it's a living organism, it was a living organism, we're going to use carbon-14 dating. So using that, we'll talk about that 52.1% is still present of carbon-14 is still present in the artifact. Okay, let's take a look at the formula. Initial amount, e to the RT, and because we've already been given the rate of decay, we can put it right into the formula. So this again needs to be 0.521, that's the percent that we're going to have that's still present, right? That's what's present. And so it's going to go from 100% down to just that, and we want to know how long that takes. So we have negative 0.0012, and again, my unknown, we want to know how long that takes. That's the t. Okay, we know we don't need this. We do know that we need to take the natural log of both sides, and you're getting the hang of it by now. So we have negative 0.0012 t, because natural log of e is 1, and I have natural log of 0.521, and I'm going to divide those, and I'm going to get that the item is roughly 236 years old. Okay, one more, two more, or one more with another little starter for you. What about the age of an artifact given the half-life? So this problem is a two-step problem. First, we have to find the rate of decay. If we have to go from half-life to rate of decay, then we can find the age. Okay? So let me just put it down. Okay, so really quickly, again, it's a two-step process. First, find the rate of decay. So I put in the initial amount becomes half as much. My rate ends up being that. It's a negative number. It should be a negative if it's going to be decay. Then I answer the question, what's the age of the artifact if 10% is still present? Here's my 10%. I set up the problem. I'm going to find t, the age. Okay? I end up getting that time is approximately, if I divide both sides by that negative 0.00079, I get 2,915 years, 2,915 years roughly. Okay, and then one last thing, if you're asked to solve a problem where it's actually a logarithmic equation, well then, for instance, something like this, let's say we know the population of wolves in a particular state is on the rise, it's increasing, and it's modeled by this formula. Population is 73 plus 18 natural log of the quantity 10t plus 1. And the question is, when will the population reach 200? Well, of course, we're going to put a 200 in for the population, and then we're going to just whittle away until the natural log, we're not using logs, there's already a log on this, we're going to whittle away until the natural log is all alone, and then we're going to get it into exponential form. Let me show you what I mean. Take away 73, and I'm going to have, oops, 127 is equal to 18 natural log of that quantity, and then I'm going to divide by